Welcome, Math-1. So I am going to be doing the rest of this review quiz. Actually, I'm going to start from the beginning. I'm going to do it all, just in case you weren't here and you wanted, like, what is Mr. Allen doing right now at this point? No. So let's go through it. So I am going to start, like, as I go through, I'm going to space this out a little bit more, so I give myself a little bit more space to do some of these questions. But you should be able to follow along pretty well, or pretty easily here, except for when my thing doesn't work properly here. So just 1 second. There we go. All right. So our first one here, so we just have to kind of recognize as you go through these that when you see these sum and difference identities like this, and you notice that the answer doesn't have any of those, we're going to want to get rid of them. So we're going to pull out our formula sheet. All right. Got my formula sheet right here. And I'm just going to find those ones. So here we got alpha minus beta for the cosine. So this first piece right here, right there, is going to become all of this. So we got, so this first one here, so that's alpha. Because of the minus sign, the alpha and beta, it's very important that the alpha and beta are specifically alpha and beta here. So we're going to do the cosine here. So cosine alpha, so which is theta, times cosine beta, which now is pi, and plus, and then we got sine alpha and sine beta, which is pi. Okay, so that there is all of that first part. And then what I'm going to do the same thing with this other one here. There's that minus sign between them, so I'm going to go minus, and I'm going to put big brackets around this one. Might be important for later. I'll put brackets around this. Whenever I do substitutions, I like to put my brackets in there because this negative here might apply to more than one thing that's inside these brackets here. So I got the sum here. So so this is alpha, beta again. But because this is the sum one, this one has a minus sign in this one. So because if this did stay around, it'd be a minus minus. It'd be turned into a positive eventually. Not too concerned though, because sine pi is 0. Okay, so we're just going to go through now and just kind of simplify this down as much as possible, because you notice these answers are pretty simple. It's like, how does this become more simple? So looking at our unit circle, 180 degrees, blue here, is right here. So this is going to be point -1, 0. So as I go through this, I say, oh, there's, why am I doing 180 first of all? Yeah, so maybe that's a good question, because it's a pi, right? So cos pi, which is cos 180 degrees, is the x value on my circle, so that's going to be -1. Now cos theta, I don't know what that is, so we'll just put cos theta. And then same thing with sine, so I got sine theta, but sine pi is the y value, so that's 0. Right? And then we got to go on this side, and I can put this in brackets here. And then what do we have? Cos theta. Again, we got a -1 for cos pi. And then over here we got sine theta. And we got a 0. Cool. So, simplifying this down, we got cos theta times -1, which is just going to be negative cos theta. Oh, that's not good. Look at these extra buttons on my card. I think it's going to throw me off once in a while. There we go. So cos theta times -1 is just negative cos theta. Here we have sine theta times 0. So this is technically just plus 0. And then we have minus, I'm going to put this in brackets here. The first one, I could put this in brackets too. Maybe I'll keep that in brackets. There you go. And then I got minus a negative cos theta. And then minus 0 times sine theta is just going to be 0. Okay, so simplifying even more down here, we got a cos theta. Here I'm just going to drop these brackets, and to drop these net side of brackets, I'm going to have to multiply this negative in to that set of brackets. So negative times negative turns into positive cos theta, and then a negative 0, okay, that's just 0. But here I got negative cos theta plus cos theta, essentially just a number minus itself, and it gets 0 in total. So there's my answer. Right? Okay, I don't have to, you can pause the video if you want to see that a little longer. Okay. All right. This one we did in class as well. I'm just going to quickly go over it again. So we got to figure out what theta is going to be. Okay, that's the solution that we're trying to find. What values of theta would equal this? It's better if I said theta is equal to in my solutions here. We got to solve for cos theta first. So I'm going to add over the root 3, and then I'm going to divide by 2. And there we go. So then I'm going to look at the unit circle and say, okay, where is cos theta equal to positive? Very key that that's positive root 3 over 2. So that makes it the longer side being root 3 over 2, because remember the cos is the x side. And it's positive in these two quadrants. So that's a really bad triangle in that quadrant there. If I go through it, all the steps, you got a reference angle of 30 degrees. Oh, my head is in the way, I believe. Let's fix that up here. Let's put that down here. Okay, 30 degrees. So we have 30 degrees in these two spots here. So we have 30 degrees, and then we have 330 down here. Now I did everything in degrees, but all our answers over there apparently are in radians. So 30 degrees is pi over 6. 330 is 11 pi over 6. So we're going to stick with that answer there. You notice there's two general solutions. Like these are kind of separated here because there's no pattern between the two answers I have. Sometimes you can connect them together, change the 2 pi to something else. All right. Question 5 here. Let's see what we have. We're trying to simplify this down. So let me just give myself some more space. I'm just going to put that right to the next page. Okay, got it. Yeah, so what we did in this one, we took all of the cotangents. It's a very good starting point. If you're kind of stuck, you're like, okay, what do I do? Let's just change all the cotangents and tangents to their respective quotient ratios, and all the reciprocals to their respective ratios as well. Okay? And then from there, just start fiddling around with some of our fraction rules. Like when you divide by a fraction, you can multiply by the reciprocal. Button's going to get in the way all the time. Okay, so we can multiply by the reciprocal. And this turns into sine over cos. And over here, multiply by the reciprocal as well. It's going to be 1 times sine over 1. Okay. And then I just start crossing things off, like here cos is crossed off, these 1's cross off. All right, and then we have sine theta plus sine theta, which is 2 sine theta, which I believe is one of the answers up there, so I'm happy. Okay. The next one here, very similar to question 1. You just got to put in the correct identity, because you notice that none of these have a minus sign inside of the brackets. So that should be a hint to get rid of them. So we're going to use one of our identities for sine here. So sine says sine alpha. That's sine pi over 2. Remember this, very important. This is alpha. This is beta here. So sine alpha cos beta. Okay. And minus, the sine one has a minus there. So cos alpha, and then sine beta. Cool. All right, so now what we're going to do is just going to, like we did the last one, we're going to find on the unit circle where pi over 2 is, because that is a number. Because if I do sine pi over 2, I'm going to get a value. So sine pi over 2, remember this is 0.01. So sine pi over 2 is just 1, so the y value, cos x. And then over here, cos pi over 2 is 0. 0 times sine x. So 0 times anything, like I said before, that's gone. So it's going to be 1 times cos. And there we go. Or I guess we put a minus 0 here. So overall, just cos x. There we go. Cool. Okay, lots of space for this question. Okay. Guess I didn't have to. For this expression here, we're just trying to find out what this value of x would be. So, like I did in class, The first thing I did, I noticed that there's no denominator on the right side, but there's this one here. So how am I going to get that to cancel out? How am I going to get it to reduce out? Well, it means I'm going to have to get rid of the sign on the top. Right? Get rid of the sign on the top there and replace it with the trig identity that sine squared is also equal to negative, or sorry, 1 minus cos squared theta. That's just the Pythagorean theorem, where it said sine squared plus cos squared is equal to 1. Okay. I put that in brackets. It's very important that when you do a substitution, put that in brackets, because when you multiply this negative in to get rid of the brackets, you're going to have a negative situation here. I'll write that extra step in there. Okay, and then 2 minus 1 is 1. All right, so now we're at this stage here. Everything looks kind of simplified at the top. It doesn't look any cleaner than it was before, but there's an option here that this could cross off. And now if it does cross off, I'm left with a 1, but there's no answer for 1. That would be misleading. So you have to remember that when you cross things off, you have to be able to cross it from every single term on the top, because essentially what this is, it's 1 over cos plus cos squared over cos, or cosine, sorry. Now I can cross things off, but I can't cross things off on the left side over here. Nothing crosses off, but on this side, I can cross one of those things off. So I'm left with a cos theta on this side, and over here I have a 1 over cos theta, which is technically a secant. Now on the other side of the equation, I have this cos theta plus an x. So these two things are the same, so therefore these two must be the other two. Because I could just like minus them over and just like minus that over, cross those off. So x has to be that secant. So I go up here and say, oh yeah, x has to be secant. I'm happy about that. Yeah. You notice what I did? I tried to keep everything on the left side, everything on the right side as I went down the equation. Let me just kind of clean this up a little bit here. No, it's not doing what I wanted to do here. Oh yeah, I messed this up completely. I'm just going to fix that. There you go. So I'm going to skip all the way down to this question here. All my numbers are all off now, so just kind of be careful. This is going to be technically question 8. Let me just see if I can actually insert that number back in there. Move that one off too. Oh yeah, I'm just really just kind of messing this whole thing up here. You gotta watch me try to fix my computer. Oh, it's right there. There's where the 8 is. Stupid thing. Alright. What? I'm stuck. Doesn't work. Not gonna fix its own problem here, so I'm just gonna have to live with it. And this one here, I'm just gonna have to set it. Okay. So this identity here, we talked about this in class, but as long as, well, not really but here, as long as these two angles are the same, it doesn't violate this identity where cos squared plus sine squared is equal to 1. Because this identity doesn't specify what angle you have. As long as you have permissible angles, this identity holds true. It's one of our main axioms for permissible values. And sine and cos have XER, so there's really no values that you could put in here to really mess this up. But as long as these are the same, like these ones are, this sine squared plus cos squared should always equal 1. So, very important. So it doesn't really matter what's inside this pi over 7 as long as they're just the same. Okay. So this next one, so you notice that over here, There's a sine 2x, there's a double angle, but all of these are just regular single angles here. So there's no way to simply just put one into the other. We're going to have to use our identities to figure out how do I change a sine 2x into my single angles here. So my angle, my identity says that sine 2x is equal to 2 sine x cos x. And then wherever there's a sine x, I can just put an m in that spot. And wherever there's a cos x, I can put an n in that spot. And it simplifies down to 2mn. All right, so down here, oh yeah, this is the trickier one. Remember we did this in class. I'm just going to show you the short version of this. So when we did this one in class, we realized that once I change this into sine over cos, because that's what a tan is. That's a very good start. Remember, if you get stuck, do that. You realize that there's a common factor on the top here. And if I factor that common factor out, I end up with 1 plus 1 over cos, which, after I change that secant to 1 over cos, it matches the bottom. So these cross off, and I'm left with sine x. There you go. So just remember, when in doubt, graph it. Graph it before. Graph this. Graph some of these answers. See what it looks like. Maybe just graph this one. You're just like, oh, that looks like a sine graph. Easy peasy. Right. Secant graphs and cotangent graphs have asymptotes all over the place, so they're obvious that what they are. Which of these is not equal to 1? So you notice down here on all my answers, 1 is not one of my solutions. So what I know about 1, like Roman numeral 1, is that it will result in a 1 once it simplifies down. Because secant is 1 over cos. Because it's squared, cos is also squared. And that's just how it works out. Like if I had tan squared, it would be sine squared over cos squared. Or just whatever happens to be, it will also be squared as well. All right, so those cancel out. It leaves with a 1. So that's not one of my answers, because I want to know when it's not equal to 1. Obviously, I already knew that wasn't one of my answers. All right, so I'm going to skip down here, because I realize, as I'm reading through the question, you should always be reading through the whole question, that I see a 1 minus sine squared. And 1 minus sine squared is cos squared. That's just using our Pythagorean identity. So that's just using this one. Sine squared plus cos squared is equal to 1. We just talked about that in a previous question. If I rearrange this, I can get it so that it says 1 minus sine squared. So it's something I can recognize, and I see that here. So that's equal to cos squared. Cos squared divided by cos squared is equal to 1. So I know it cannot be 3, so I'm just going to cross the ones with a 3 in them. So now my choice is between 2 and 4. So I'm not going to check 2, because I already know 2 is not going to work, because that's what it says down here. It's not going to turn into a 1. So what I'm going to do for this one is now I'm going to see if this one is a 1 or not. Okay, so look at my formula sheet, and I realize I see a 1 plus cotangent squared. I'm not going to worry about the sine part yet. Maybe I'll have to change that to the cosine version like we did up here. So I'm not going to worry about that now. I'm going to worry about the top, because the top, 1 plus cotangent, is the same as secant squared theta. And then on the bottom we have sine squared theta. Okay, so good rule of thumb is to get rid of reciprocals. So I'm going to change that to 1 over sine squared, because this one's squared, that will also be squared. Okay. And a very common mistake here is to cross these off. Can't do that, because you have to assume that this is over 1. So when you divide, just like when you divide by 2, you times by a half. Right? It's a half what it was before. So when I divide by sine squared, I'm timesing by the reciprocal of sine squared, which is 1 over sine squared. This just turns into 1 over, head's in the way there, I turn into 1 over sine to the power 4 theta, which is definitely not 1. It could be 1, depending on what theta happens to be, but it's not always 1. So I'm going to just cross that one off. Well, I want to know, so the wording of this question is a bit bad. Okay. We want the ones that are not equal to 1, so that's definitely not equal to 1. So that's one of my solutions. So that's the one I need. So it's got to be this one, because I'm assuming that one's also not equal to 1. Again, when in doubt, just graph them. Okay. Simplifying this one. This one, we simplified this one also in class. You have to remember that the top and the bottom are kind of independent of each other. So when I go sine x over cos x, and I times that with cos x, which is technically cos x over 1, I'm allowed to just cross these off now because they're on both one numerator and the denominator while they're in the numerator. It's kind of strange. Okay? And then the bottom, I can do the same thing. This is going to be 1 over cosine x times cosine x over sine x. And again, now I can cross these off. Okay. Now be very careful. Like this sine x is in the numerator. Okay, so maybe I just make my head just a little bit smaller here. Okay. So we have sine x over 1. And the bottom, this sine x is in the denominator of the denominator. Okay. And then when I flip them all over, or multiply by the flip here, I just have to write it down here. It's sine x over 1 times, sine x over 1. So sine x times sine x is sine x squared. Cool. All right, so this is where the questions started deviating. I'm going to probably skip through 3D here, but this is where the questions start deviating from the answers that we had before. Oh, actually, I'm not going to skip over question 4. I'm just going to graph that one, because up here it doesn't say how to solve them. Okay. Okay, so here my first question. I think it's label number 1 as well. Yeah, it's label number 1 in the handout. I'm going to be using those identities again, so this Cos Difference Identity. I have theta and beta, theta and b here. Key is I know that they're both in the same quadrant. We'll see why that's important later. But when I break up this Cos Difference Identity here, I'm going to get cos alpha, which is theta now, and this is alpha, and this is beta. So I get cos alpha, and then this is cos beta, plus sine alpha, sine beta. Okay. Now, here it's just saying that if I see a sine theta, which is right here, I can replace that with a 7 over 25. If I see a cos beta, which is right here, I can replace that with a negative 9 over 41. The problem is, what is sine beta and what is cos theta? Well, the thing is, I just need to know more information about the triangles at those angles based on these ratios that I have here. So what I kind of know, because remember sine is like opposite over hypotenuse, that the hypotenuse is probably going to be 25 for theta. And beta, the hypotenuse, is going to be 41. I just need to know, like for here, what's the opposite of beta and what's the adjacent of theta. So what I'm going to have to do now is I'm just going to have to draw these out. Now the next key part is that they are in the same quadrant. So that means I got to figure out where is beta negative, or sorry, cos negative, and where is sine positive at the same time. So sine is positive in the upper two quadrants. So it can't be in the bottom two quadrants. So I can cross those off. And cos is negative in the left quadrants. So I can cross those off. So I can do that, right? Cross that off. Cross that off. Oh, I'm left with just that one quadrant. So both my triangles are now in this quadrant. In this quadrant. Okay? Now, based on what I know about theta, remember it's opposite over hypotenuse. That means the opposite is 7 and the hypotenuse is 25. And what I know about beta is adjacent, so it's negative 9 over 41. So my adjacent is negative 9. Then we just do a quick little Pythagorean theorem here. And these are right angle triangles, so that's allowed. Beep, 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 beep. And I get 24 for the adjacent side, so I didn't draw this to scale. Remember, that's negative, because it's going backwards. That's the same reason why this 9 is negative. And the other one, I get 40. But that one's positive because it's going up. All right, so now we know that, so I go over here. So theta, remember theta is adjacent over hypotenuse, and beta is opposite over hypotenuse. There'll be plus sign between them. Plug all this in your calculator, you're going to get an answer. Because there's no square roots or anything, I don't have to worry about trying to simplify things down, finding common denominators. But the common denominator is 25 times 41, which is 1,025. And if you want to just show the steps, you can. So like this left side becomes 216, and the other side becomes 280. Because they already have the same denominator, you could just add the tops together like this, and you get 496. Okay. But if you just typed in your calculator, went math, enter, enter, you would have got the right answer too. The reason you want to do it this way is if there were like square roots in your answers, and you had to have an exact answer. But we just wanted 2 to the nearest hundredth actually, so I'm actually going to divide it. I'm actually divide it through. So this is approximately 0.48. Almost a half. The fraction looks weird, but the decimal's pretty nice. Okay, so this next one is one of those solving ones, but remember when we're solving it, you're going to see that later on too, when we're solving it, we want all our equations to have very similar ratios to them, right? If they're not the same ratio, try factoring first. If you can't factor it, then you're going to have to change the ratios to be all matchy-matchy. Now the fun thing about this one, they're already matchy-matchy. It's all cosecant, so that's good. Okay, so I'm just going to, over here, I'm just going to write a quick little let statement here. So CSC x is equal to A. So what I'm going to do is I'm going to replace all the cosecants with A's. And then, oh, I got a quadratic, so I'm just going to make this equal to 0. Then I'm going to factor it. What multiplies that? So it's 2 and 1, both negative. So A is 2 and 1. Okay. Remember, it's not A that we're trying to solve. We're actually trying to solve cosecant. So cosecant x is equal to 2, or cosecant x is equal to 1. Okay? But again, I don't have a cosecant button. I don't know where these would be on the unit circle. But I know that cosecant is sine, is the reciprocal sign, which means that sine, if cosecant is 2, then sine is the reciprocal of 2. It's a half. And then the same thing with this one. You can flip over, the reciprocal of 1 is just 1. So if I solve these two equations, I solve the ones above it, because they're just reciprocals of each other. So, we'll pull out our little unit circles here. Okay, so what angles is sine equal to a half? If you did this, your reference angle would be 30 degrees. So it's positive. So it's here in this quadrant, that's 30 degrees. And it's over here, this quadrant, which is, this sine is positive in those two quadrants, 150. Okay, so there's two answers. And then over here, where's sine equal to positive 1? Remember, sine is the y values. So up here at 0, 1, that's 90 degrees. So my answers here, x was 30, 90, and 150 350. I just wanted to stop myself at 360, so this is all we have. You want to verify them, we put them in there, but the problem is you don't have a cosecant button. You have to do a bunch of 1 over sines. That's okay. Okay. I'm hoping I have enough space here for all these questions. This one here, it says it's equal to, so it either boils down to a single number or simplifies down to something a little bit nicer than what you see here. So I see a bunch of secants and cotangents and a bunch of other things like that. There's no common denominators here. You could try to do that first, but I probably want to see if I can simplify down any of these fractions before I start trying to add them together. So let's see what we have here. Yeah, okay, I see that this could work. So I'm going to put x's in there. And then over here we have cotangent. Cotangent is cos over sine. Remember, this is squared, because that's cotangent squared. Okay, and then on the bottom, oh, right, this looks nice too. I like that. I like that how both these in the denominators. When you do your KFC, the flip and multiply part, so I'll show you on this one over here, because they're both in the denominators of their respective pieces, like this cos squared's down here and this cos squared's also down here, when I do my KFC, it'll flip over and be in the numerator, too, and cross off. So I'm left with a sine squared x here, that's the first side. Okay, on this side, same thing's going to happen. So I'll just show the step, but you could just cross them off up here. Okay, cross off, cross off. Hey, look at that, I'm left with a cosine. Hey, that's just equal to a 1. There you go. Remember, sine squared plus cos squared is equal to 1. That was shown up before, Pythagorean theorem. That's how it works out. So it just ends up being a 1, which is kind of nice. This is probably going to be the same thing. Maybe this is going to boil down. And I can kind of see some things already crossing off here, because cotangent and tangent, they're reciprocals of each other. It's like 2 times a half is 1. 3 times a third is 1. These are just going to cancel each other out. I'm just going to cross them off right now. All right, so now we're left with 3 cos x times 2 secant x. I'm just going to rewrite this as 6 cos x times 1 over, 1 over cos x. Look at that. Yeah, they're going to cross off as well because they're reciprocals as well. And I'm left with a 6 as an answer. Perfect. Happy about that. That's what's going to happen here. So we got a 6 here, we got a 1 there. Question 5 is pretty much the same. If these were to kind of boil down to a single number, can I arrange them in order? Just make sure I have enough space here for those questions here. Okay, so it's taking a bit of time here. Okay. Some of these are pretty easy, like here, sine and cosecant, they are reciprocals, just like this question up here. They're reciprocals of each other. They're just going to cross each other off. So these, if I were to write it out, I should just write it out. I should give myself some space here. Okay, I'm giving myself lots of space. So if I were to write this out, I would get 1/3 times sine theta times 1 over sine theta. Sine theta is crossed off. So this last one is 1/3. So that's my value for that. For this one here, I'd factor the 2 out. Because there's a common there, I always like to factor first. And then I see sine squared plus cos squared. That's equal to 1. So this one's equal to 2. That's 2 times 1. And I'll just highlight that. Okay. This one here, I could either change the tan to be sine over cos, or I could just change the sine over cos to be tan, but this will end up being tan theta minus tan theta. No, that just ends up being 0. Okay, so that just That's that, turn into that. Okay. Okay, and let's see what we have here. We've got tan squared minus secant squared. What do we have here? Tan squared, secant squared. Oh, there's an identity here that says secant squared. Let me just write this out here. That secant squared is equal to 1 plus tan squared. You always think in a couple steps in advance because you think, oh, there's a minus sign here. So technically what we're doing is we're minusing this 1 and we're minusing this tan squared. So we have a tan squared minus 1 minus tan squared. So the tan squareds are going to cross off. And I'm left with a negative 1. Cool. We found all the values. We just have to arrange them from smallest to largest. So the smallest is negative 1, so that's 1. And then we have the next smallest would be 2. So this is the smallest value. The next smallest would be a third, so that'd be a 4 there. And then the next one, the biggest value we have here is equation 3, so that's the largest. There you go. Cool. Just do a highlighting thing I'm doing here. Highlight, that's my identity used. Okay. Okay, so we're going to solve, there's a lot here. Okay. We're going to solve these here. Now I'm going to try to do the solving algebraic if I can. Okay? If I can't, then we'll deal with it graphically like this. Not impossible to solve D algebraically, but I'm just going to solve it graphically instead. Okay, that's good. So, cotangent, blah, blah, blah. So remember what I said before, you want to make sure they're all matchy-matchy. They're all cotangent, so I'm happy there. So what I'm going to do is just make this equal to 0. So I'm going to add over the 1 and make this equal to 0. The reason behind that is because this is squared. If I were to do a let statement, it'd be like a squared plus 2a plus 1. If you want to just put on that side, you can. A squared plus 2a plus 1. That would factor out 1, a plus. Oh, that's a bit easy. Okay. So when a is equal to negative 1, this would be equal to 0. So based on that, cotangent. When cotangent theta is equal to negative 1, we are in a good situation. But remember, cotangent is the same thing as the reciprocal of tan. So really, we just want to solve for when tan is equal to negative 1. Where's tan equal to negative 1? So tan is negative in this quadrant and this quadrant. It's equal to negative 1 with a reference angle of 45 degrees. I want this to be in radians eventually. So pi over 4. So we're looking for these two angles here that would satisfy this one. So we got 3 pi over 4, which is this 135 here, and then 315. What's 315? That's I don't know actually. Why am I blinking on that one? 7 pi over 4. So my two thetas here, 3 pi over 4 and 7 pi over 4. That's it. You're going to get you get the two solutions, but there's only one thing you have to solve in this one. All right, question B. Remember what I said before, if they're not matchy-matchy, try factoring first. If you can't factor, try using the identity to switch it. So here I can start factoring here. I can say cosecant, let's just factor that out, bracket, bracket. And when I factor, remember division, so you just kind of divide out the cosecant theta. But cosecant theta divided by cosecant theta is 1. So that's very important. That turns to a 1. So this is just me factoring. So we're actually solving two equations here. When is cosecant theta equal to 0? And when is cosecant minus 1 equal to 0? So actually, cosine, sorry. We're just trying to find out when that's equal to a half. Now this one's easy over here. When is that? When is this going to happen? Cosine's positive. That's okay. So positive is going to be this quadrant and this quadrant. Reference angle is 60 degrees this time. So my two solutions over here would be pi over 3 and what's that? 60, 300, 5 pi over 3. Just kind of blanking on some of my unit circle stuff here. Okay, so that's over there. Now over here, we're trying to solve cosecant. Cosecant is sine. I'm going to do the reciprocal of this, and I get 1 over 0, which is undefined. Now remember, sine is never undefined. Why? Sine has all the values. There's no restrictions to theta, so this could never happen. All right? How can I ever solve this question? Sometimes like tan is undefined because technically allowed. Cotangent can be undefined because of the math behind it. But the hypotenuse could never be 0 based on this math. This doesn't work anywhere. So there's just no solutions to this one. No solutions to this side. So my actual answer is just these ones over here. Okay. Now, like I was saying, you want to make sure that everything is matchy-matchy. Oh, it's not letting me do that. Okay. So this one I can't factor it out. There's nothing in common between these two. So what I'm going to have to do first, because I can't factor it out, I'm going to have to switch this cos squared here to 1 minus sine squared using that identity that we've done before. All right? So I just kind of switch this piece out and I put that one in there instead. And that's 2 there. Remember, I'm using brackets. And make sure you're being smart and pretty liberal with your brackets here. So I'm going to multiply the 2 into the brackets. Minus at the same time, because I see a square here. It's going to be quadratic. Let's minus this 1 over. Let's move that 1 over to the other side. Okay. If I reorder this a little bit, I get negative 2 sine squared minus sine x. And 2 minus 1 is a 1. So 0. And the problem with this is I don't like having negatives in the front here. So I can just times everything by negative 1 and switch all of their signs. Or I can move everything to the right side. I can factor out a negative. Lots of things you can do to fix this. But I want that positive in the front. And then I'm going to factor this. So I'm going to have 2 sine x here. I'm going to have a 1. I'm going to have a 1. The sine x here. This is just me kind of doing some mental math here. But you could just factor it like you usually factor it. And this would be a positive. This would be the negative. Yeah. Okay, so when is sine x equal to a half? And when is sine x equal to negative 1? So you solve both of these for the first circle again. So sine x is equal to a half. I'm just going to do that over here. So sine x is equal to a half at 30 degrees and 150. We'll just write those down. Pi over 6 and 5 pi over 6. And when is sine equal to negative 1? So negative 1, it's equal to negative 1 straight down. So that angle is going to be at 270, which is going to be 3 pi over 2 as my answers. Okay, cool. Now, what I don't like about this next question is how ugly it is. There's a lot of double angles in there. What you could try to do is try to get rid of the double angles, but it's really, really hard to do that. Okay? Because as soon as you try to get rid of them, you add in sines and coses, and then which of the cos double angles do I use? Now, nowhere in this question does it say solve for theta algebraically. It's trying to find exact values. But if I solve these in degrees, I can always just change into radians exactly as well. So what I'm going to do is I'm just going to plug it all into my calculator. So I'll just type it over here, and then I'll show you what it looks like. So I've got y is equal to, let's get rid of some of this stuff here. So 4 sine 2, oh, I should probably put a 2 there, 2x, bracket cos 2x, bracket, oh, and then plus 1. And that's equal to 0, so I'll put a 0 there. Okay, so there's my equations I put in here. So I got 4 sine 2x cos 2x plus 1, and then I got a 0. But I am, hit graph. Perfect, and you see all these answers down here. I'm in degrees, which is what I want, because you usually get nicer degree numbers, but we could switch into radians later. I want my window to only go up to 360. I'm dealing with degrees right now. So I'm just going to make sure my window stops at, oh, there's at 360. So I put a bit of answers here. Okay. So I've got my graph. So I have 1, 2, 3, 4, 5, 6, 7, 8. Usually with double angles, you do get lots of answers. So, second trace 5. Enter, enter. I'm going to guess 45 to start off with. So that's my first one. So my first x is 52.5. So I'm going to actually write that over here. 52.5 degrees. And then I'm going to do it again. Second trace. Enter, enter, and then I'm going to guess something about 90 this time. So I get 82.5. Remember, you can always just cursor side to side. So when you do the second trace 5 here, you go enter, enter. You can just go sideways until you get it to around where you want it to be. So somewhere about there. So 142.5, and this, it's going to get tedious. Now, I could do them all. Maybe I'll do them all because I want the answer key. Okay, second trace 5. Enter, enter. I'll guess 180 this time. It's 172. There's a pattern here. You notice what the pattern is. That's great. Okay, and I'm going to add, pretty much add 90 to all these answers. Yeah, I'm going to add 90. So, oh, go down to 90 plus 90. So I should get an answer here of 262.5, and then I'm going to get. If I add 90, am I going to be within my thing? Yes, I am. So I'll get 3, I'll just write it over here, 352.5. Now, I don't know which is faster, me adding 90 to these things, or, because I see the pattern when I was in the picture here, or just finding the answers. Then we'll have 232 here, 5. And then I'll just do that again. So 322.5 degrees. Okay, now what we're going to do, we're going to change these all to radians. Now that's a lot of work. You take all these answers, or it's just a lot of tedious work. You take all these answers, divide by 180, get some fractions here. So my first one here is going to be 7 pi over 24. That's garbage. And then we're going to do it again. We're going to get 11 pi over 24. These are all exact values, all in radians. I'm just dividing them by 180. The calculator turns them into fractions for me. You'll have to go math, enter, enter. Oh, I don't know why I put 180 there. I said I was divided by 180, so I wrote 180. Cross that off. 24 there. Okay. So 23 pi over 24. Oh my lord, this is going to be taking a long time. So maybe you could skip across here. I'm going to complete this, but you could skip ahead and just go to the next question. If that's what you're here for. Unless you're just here to hear me talk. Oh, yeah, that's right, I kind of jumped a little bit. Which one am I at now? I'm trying to figure out why that was so close to 2 pi. They're just out of order. There you go. All the answers. Very ugly. Now, I wouldn't expect you to be able to answer that the regular way. This is the old school math, old math 30 would be able to solve that, but not this math. Okay, let's scroll down here. We want to verify these, state restrictions, and prove. Verify, prove, exact values, and that's it. Okay, just want to see where I had a B here. So, proving, I don't know if I'm going to have enough space to prove these. I'm just going to push that to the next page. Give myself a little bit more space here, plus for the restrictions. Okay, so the verifying, give myself space for verifying. Right. We're just going to use the unit circle to help us out to see if the left-hand side is equal to the right-hand side for 30 degrees. Remember, this is just 30 degrees, so I could just imagine that on my circle. I might as well just draw the circle now. At 30 degrees, I have a point of root 3 over 2, 1/2. Okay. So I'm going to use that to help me figure this one out. So sine. Sine is the y value. So this is for the left side here. I'll put a little equal sign right about here. So sine is 1/2. So I'll just replace that. Here's another sine. I'll put a half there. And then cotangent, which is going to be squared. Remember that is... Look up there. Cos over sine. So cos is the x value over the sine. Right? You can do the whole flipping blah, 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 but this will just kind of cross off here. So I've got 1/2 plus 1/2 times root 3 over 1 squared. Okay, I'm just going to keep on simplifying this side down until I get a nice answer. So we got 1/2 plus 1/2. When you square this, it turns into a 3. So we got 1/2 plus 3/2, which is 2. Okay, so I want to give myself a little bit more space here. No, I lost that. Okay. So this will end up being 2. Okay, now the goal is to get the other side to be the same, right? Hopefully they are the same. Otherwise, if this is false, then what's the point of proving it? Cosecant, remember cosecant is 1 over sine. So it's the reciprocal sine, so it's 1 over sine theta. So I'm just going to take whatever sine is and flip it over. So sine is 1/2. Oh, that's 2. There we go. So check mark. I'm not going to write that LS is equal to RS at this point. It's just I verified it. It's right. I'm happy for that angle. Now remember, I can only prove it for the permissible values. So the restrictions here are very important because I want to know what are the non-permissible values. So maybe for later I can check them out. But we got this cotangent, we got this secant here, or cosecant, sorry, that's going to be the problem. So what I'm going to do is I'm just going to kind of rewrite what we have here in terms of their quotients. Remember, cosecant or cotangent is cos over sine. This is going to be useful for proving. I could see something crossing off here, which is going to be nice. And then on the other side, we have 1 over sine as well. 1 over sine. Okay. So I'm just looking at denominators here to figure out what are my restrictions. So I can't divide by 0, so I don't want sine theta to be 0. So what values of theta would cause that? So it's my circle. So where are my y values equal to 0? So I got here and here. This is the one the y values. Remember, it's -1, 0. And this is 1, 0. There's no restrictions here. So there's like no domain restrictions. So I'm going to put a general solution here. So I can see there's a pattern between my two answers, 0, 180, 360, etc., etc. We start off with radians. Let's stick with radians here. So my theta values cannot be 0 plus whatever my common difference happens to be. So it looks like I'm adding pi or 180 each time. So pi n n e I. Remember, that can also just be simplified down to pi n. N e I. Man, I'm taking a long time here. Okay. Hopefully, again, my son's medicine. I don't know when the pharmacy closes. I'll have to figure that out. So the next one, we're going to prove it. So we already have the kind of the starting position up here. And when I did this to find those denominators, I can realize, oh, some things would start going to cross off here. So hopefully that's going to help me out with this question. I don't think I missed a square or anything, did I? No, I didn't miss any squares. Okay, so that's how I'm going to start this one off. So I'm going to put my sine theta here. I'm going to put my sine theta here, and then here I'm going to go cos squared theta sine squared theta, and on the right side I'm going to go 1 over sine. Now, the more complex side right now is the one on the left, so I'm trying to figure out, can I boil that side down to end up being that right side? So I'm going to try to keep everything I can on one side of this equation, left side on the left side, right side on the right side. So I can't do anything with this sine theta here. So here I'm just going to start crossing things off here. What do we have? So I'm going to cross one of those off. So I'm going to have a cos squared theta over sine theta still. Okay. So notice this is just one fraction. So this is going to, I'm going to change this to one fraction. So I'm going to take this over here and times it by sine theta. But I had to do it at the top as well to make sure I have a common denominator. And as you're doing this, you've got to be thinking, is that going to help me? Like, what is up here now? So on the top, I have sine squared. Oh, sine squared plus cos squared. Nice. And because of that, sine squared plus cos squared, actually, I'm just going to write it out. Sine squared theta plus cos squared theta. Put your wrinkle in there. 1 over sine theta, because remember, this will turn into that Pythagorean theorem. Because these two sides are equal to each other, I didn't even have to touch the right side. I can write down QED, left-hand side, and go to right-hand side. So it's going to be true for all permissible values. Cool. Next question. Prove. I'll prove this one. Okay. Maybe I'll just give myself a little bit more space here. So a good rule of thumb here is get rid of reciprocals if you can, if that's going to be useful. You can see on one side you have just signs, the other side you have reciprocals, so it's probably a good idea to get rid of those reciprocals. Watch, this one's squared, so this is also squared. Another rule of thumb is that conjugates are usually your friend in these kind of questions. And I can kind of see that the conjugates are going to be kind of nice for us, because on this side of the equation, on the right side, to make this thing kind of matchy-matchy, I can change this cosine squared to a 1 minus sine squared. Which is that difference of squares that we had before, right? So that's the difference of squares. And you can see on this side, the denominators are essentially just difference of squares. So what I'm going to do is I'm going to find that common denominator, which is the difference of squares, the conjugates here. I'm going to do that to the tops and the bottoms. So I'll do that one over here, 1 plus sine. When I multiply out that denominator, I'm going to get, actually I'll write it out first and then I'll multiply it out. I'm going to get that times this, the conjugates. And that is going to multiply out to 1 minus sine squared theta, which is good. Now I'm just hoping the whole top just becomes a 6. Let's see what happens with this top part here. Okay, so I'm going to multiply the 3 into the brackets here. So I'm going to have 3 plus 3 sine theta. And in the other one, I'm going to have 3 minus 3 sine theta. So I'm multiplying this 3 into the brackets, and this 3 into those brackets over there. Oops, sorry. Into these brackets. And I'm going to get these more complex statements. But I got 3 sine theta minus 3 sine theta. They're going to cancel out. But then I have 3 plus 3, and I get 6. Q, E, D. Perfect. Don't have to worry about non-permissive values because they didn't ask for it, so why bother? But conjugate pairs are useful. Okay, keep that as in tips. If you ever see these sine squareds or you're looking at this difference of squares, can I make the other side a conjugate pair or something? Okay, so the last one here, find the exact value of tan 75. Okay, now 75 is not one of those 12 angles that we have on a unit circle, but it can be made up of those 12 angles from a unit circle. So I can use 90 and, no, I probably didn't want to do that. 90 minus, no, that's not going to work. 120 minus 45? Yeah, 120 minus 45. Okay, so I'm going to go 120 minus 45. Okay. Now, lots of different angles can add up to that, right? Or subtract down to that. I just picked these two because of the first ones I found or thought of. And then what I'm going to do, using the unit circle eventually at 120, which is right about here. That's about 120, right? And the point being negative a half root 3 over 2. And then using the 45 as well. Root 2, this is 45, I should say. Root 2 over 2, root 2 over 2. Now remember, if this is in radians, just turn it to degrees. It makes it a little bit easier to try to figure out how to get the answer. So let's see what we have here. So according to my tan difference alpha minus beta here, it's going to be tan alpha minus tan beta. Yeah, tan beta. All divided by 1 plus tan alpha tan beta. Okay, so that's the difference identity for tan. And then what I want to do is I want to figure out what is tan 45. Tan 45 is an easy one. Tan 45 is opposite over adjacent. 1, because they just happen to be the same. Tan 120 is a little bit trickier. Still opposite over adjacent. But it's going to be root 3 over 2 over 1/2, which ends up being negative root 3, because the 2 is going to cancel out here. Okay, so negative root 3. So wherever I see a tan 120, I'm going to put a root 3 in that spot. So here's a negative root 3, sorry, very important. Wherever I see a tan 45, I'll put a 1. There's that part. And then I got 1 plus on the bottom, a root 3 and a negative root 3 here, and a 1. Okay, I'm going to just kind of simplify this down a little bit. Negative root 3 minus 1. 1 minus root 3. I'm just thinking about, should I rationalize this or not? So I don't think it's a nice number. Because they're not exactly the same. They're not opposites of each other. So negative root 3 minus 1 divided by 1 minus root 3. Oh, it does simplify down to something nice. Okay, let's rationalize it. We have enough space here. So remember, to rationalize, we multiply by the conjugate. So 1 plus root 3. 1 plus root 3. So when you multiply out the bottom piece, 1 times 1 minus 3. So my bottom is going to actually be a negative 2 here. So I'm using the whole rainbow property here. So 1 times 1, 1 times that, blah, 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 blah. Because these are conjugates, it's going to turn into a difference of squares. So that whole middle term cancels out. So that root 3 times root 3 becomes a root of 9, and the root of 9 is just a 3. And 1 times 1 is that. So it's negative, sorry. So we get negative 2. On the top, so what do we get on the top? So we're going to get a, I'm going to do the whole rainbow as well. So root 3 times 1. Negative root 3 minus 3 minus 1 minus root 3. So I got 2 negative root 3. So that's negative 2 root 3 and then minus 4. Then I can realize I can divide all of these things by 2. Remember, you had to make sure you could divide everything by 2. If I do that, or negative 2 specifically, I get root 3 plus 2. Remember, when you did this, like, I'm going to put on the side here. I'll put a plus there. Negative. You have to divide both the pieces by negative 2, and if you can do that, then you can divide them all by negative 2 at the same time, and then you get this answer over here. All right, there we go. Ooh, that was an hour. I gotta go. I'll see you guys all tomorrow. Good luck studying. Bye.